Continuing to work through our sample problems that are really applying our type 1 and type 2 equilibrium problems now to acid-base chemistry. This again is a more typical kind of problem that you'd see. We wanted to look at a weak acid, and again we know that this is a weak acid because we see this COOH, that carboxylic acid functional group, so we know that's a weak acid. Again, we're going to abbreviate this as HPR to make kind of our chemical equations and equilibria simple. So again, being a carboxylic acid, salts are used to retard mold growth in food. Again, just a little backstory. Here's the relevant information that we need. What is the H3O plus concentration of a 0.1 molar propanoic acid solution? And they give us the equilibrium constant. So again, we're going to treat this just like we did all of our equilibrium problems from chapter 17. The first thing that we're going to do is we're going to write a chemical equation. And again, we're abbreviating this propanoic acid as HPR. So HPR, when in water, is going to dissociate and make H3O plus and its conjugate base, PR minus. Because we're showing the chemistry here of an acid dissociation process, we're going to write Ka. Ka in this case is given as H3O plus times PR minus over HPR. In this case, it's equal to 1.3 times 10 to the minus fifth. So they give us that. So again, write the equation first, write your equilibrium expression. In this case, we're talking about acid chemistry, so we're going to write a Ka. And we know that the initial concentration of HPR is equal to 0.1 molar. So we're going to make our ice table here. 0.1 molar HPR. Water is not part of our equilibrium expression, and we're assuming negligible concentrations of H3O plus from water, and there's no other contributions to PR minus. So in this case, our equilibrium only has one direction to shift. And our equilibrium expressions are 0.1 minus x. Some amount of this is going to go away, and it's going to generate the same amount of H3O plus and PR minus. So now this becomes just like a lot of our other problems. We're given an equilibrium constant of 1.3 times 10 to the minus fifth, and that's equal to the concentrations of these species. So H3O plus, PR minus, and HPR. So x, x, and 0.1 minus x. Because we have a small equilibrium constant, we're going to make the assumption. So assume x is small. And so this simplifies to x squared over 0.1. Makes our algebra much simpler. And so we can solve for x, and that's equal to 1.1 times 10 to the minus third molar. And that's equal to H3O plus, right? And that's what this problem is asking, what the H3O plus concentration is. Problem could have an extra little step if we asked for what's the pH of the solution, or what's the OH minus, or the POH, okay? But pretty straightforward. But remember, anytime you make an assumption, we have to do a check. So I'm going to call this a post check, okay? So the post check means you figure out what your x value was, and then you put it over whatever your concentration was initially. And we have to make sure that with this post check that this value is less than 5%. So the amount that we're saying was small and subtracting off of this value, we need to make sure that it's not more than 5% of it. So we need to take that value, put it over what the initial amount is, and just make sure that it's not more than 5%. So in this case, it's 1.1 times 10 to the minus third over 0.1. You multiply by 100 to make it into a percent, and that's 1.1%. I'm going to show you another little trick that I'm going to call a pre-check here. So our pre-check is something you can actually do before you start your problem. And as long as you do the pre-check, you can make this assumption right away. But I need to see some sort of check in your problem to make sure that you are validated in assuming that x is small. So this pre-check, if we call this one the 5% rule, we're going to call our pre-check the 400 rule. And what this really does is it basically is going to take your initial concentration and divide by your Ka value. So again, what this means is as long as we have a large amount of acid and a very small equilibrium constant, we can run into a situation where we'll be fine making our assumption that the amount that we're taking off is small. So specifically for this problem, we're going to have 0.1 as our starting. The Ka is 1.3 times 10 to the minus fifth. And again, running through this, 0.1 divided by 1.3 times 10 to the minus fifth gives 7,692. So certainly both of these, whether it's a post-check or a pre-check, show that we would be validated in assuming x to be small and simplifying our algebra. So again, whether you want to make the assumption and then do the post-check with the 5% rule, or you want to kind of check ahead of time and see whether or not your assumption would be valid. Either one of these I need to see in order to have full credit on a problem if you're going to solve it algebraically by making an assumption that x is small. And because we're working with weak acids and weak bases that generally have small equilibrium constants, this is often going to be the case.